All right, in the previous example, we spent a lot of energy showing that removing 4 minus 3, 1 from the set of generators would not change the span. So really, if I go back, we were given the span of 3 vectors that were linearly dependent. They were actually coplanar. And we wanted to show that removing that third vector didn't change the span. And so we have this basis here containing only the first two. First part was easy. We got rid of redundant vectors, and so we did get something that was linearly independent. But we had to work a bit harder to show that because V3 could be written as a linear combination of V1 and V2, we could actually get rid of it. And the reasoning we use is not specific to the vectors we had in this example. It would work for any sets of vectors. And so what I want to do now is to avoid repeating this argument for every example, let us recap what we've learned. All right, so here's a takeaway. Consider A, which contains vectors v1 through vk, and assume that vi, so one of them, can be written as a linear combination of v1 through vi minus 1, vi plus 1 through vk. So exactly A, but without vi in it. Then the span of A, that's A, is the same as the span of v1, vi minus 1, vi plus 1. So I'm removing vi from the list, vk. All right, so that's what we did in the last example. V3 could be written as a linear combination of V1 and V2, and so I could get rid of it. This tells you that you could get rid of VI because you could write it as a linear combination of these k minus 1 vectors. All right, so using this takeaway, we may remove any vector from A that can be written in terms of the other vectors in the set, the vectors that we're keeping. Looking at the start of this last example, we find this reduction. And I claim that this reduction actually gives us the whole picture. All right, so from this reduction, if I look at only this part, if I remove this and pretend like this is the system I was solving, I get that the third vector was twice times the first and 1 times the second. All right, so that's what we got. If I go back, that's what we got over here. In general, we could write any of the vectors corresponding to a free, I want to say a free variable, but free column, in terms of the vectors corresponding to leading ones. All right, so the third vector was corresponded to a free column, so in some sense I could write it in terms of the two vectors that corresponding to leading ones. It was redundant, and using the takeaway I could get rid of it. All right, so here's a method that we sort of use but without knowing it. So if I want to find a basis for the span of v1 through vk, what I'm going to do, just like we did in the last example, I'm going to put v1, v2 up to vk as the columns of the matrix. And I'm going to reduce this matrix to REF and RREF, whatever you want. All right, so this is this step here. Now, once it's reduced, I'm going to keep the vectors, so let B contain only the vectors v1 through vk, whose columns corresponds to leading ones in either reduced matrix, either REF or RREF. This B is a basis for S. That's it. Reduce, keep the columns corresponding to leading ones. Now, if you go to RREF, you get a bit of extra. So each free column in the reduced matrix RREF, so you do have to go to RREF here, gives the coefficient necessary to write the corresponding vector as this is what we have here. That column gives you the coefficient to write the corresponding vector as a linear combination of the elements of P. All right, so let me explain this last point a bit more. The reduction needed to write a redundant vectors in terms of the vectors of the basis is included as part of the bigger reduction of the matrix H to R, R, E, F of H. You simply need to ignore the columns of the other redundant vectors. So here we didn't have any other redundant vectors, we just ignored the zeros and we got the correct reduction. Same thing. You simply, in general, the elementary row operations preserve any linear dependencies between the columns. So if you start with column 5 equals column 1 plus 2 column 2, when you reduce, that relationship between the columns will always be there. So in the reduction, column 5 will be column 1 plus 2 column 2. All right, so in the next example, we'll look at this method and apply it to this question.